Okay, let's get started. Okay, so previously we saw that the EPR argument demonstrates a conflict or precisely a contradiction between the assumption of locality assumption that quantum states are complete of the real physical situation. And the assumption that QM is correct. Okay, so the idea is their point was to, their goal was to disprove the assumption that the quantum states are complete, taking for granted locality could be enforced, and the quantum mechanics is correct. But now, in hindsight, it's more interesting to think about EPR as a demonstration, in fact, that there's a conflict between the assumption that quantum states are complete, well, as a problem with locality. And the reason for that is because Bell came along in 1964, I think that's the right year, demonstrates a conflict between the assumptions of 1, locality, 2, quantum states are incomplete, and 3, quantum mechanics is correct. By correct, I mean its predictions are validated experimentally. Okay, so how does that work? Yeah. The EPR argument, basically, you assume you have, okay, we'll do the Bell version of their argument, which is essentially that I start out in a singlet. So the singlet produces anti-correlated pairs of photons or electrons, spin half of electrons. And there the idea is that when you partial trace over one or the other system, you're left with the identity state. So as far as, if Alice gets half of the pair and Bob gets the other half, then the quantum state on Alice's side is identity, and the quantum state on Bob's side is identity. Now, if Alice makes a measurement, using a von Neumann ideal type measurement of her particle, then she does a projective measurement, her state will collapse, be updated to, whatever, up along the direction she measured. Now, we saw that as an instance of Bayesian update. We can understand that as Bayesian update. But remotely, on Bob's side, his quantum state also changes. So now if you assume that quantum states are physical, then the physical state of affairs at Bob's side has changed as a consequence of what Alice chose to do or not to do on her side. So if they're space-like separated, then clearly the quantum state is changing non-locally. If you assume quantum states are complete, then the physical state is changing non-locally. Now, of course, because I've argued that you can think of the state update rule as a kind of Bayesian update, then if you think of quantum states as informational, as just information, then it's completely natural that Bob's information gets changed as a result of Alice's information. In other words, if we have two classical particles that are pointing back to back in some random direction, the fact that Alice learns what direction her particle is pointing in, it's completely natural that now we know that the state at Bob's end, his knowledge, if he finds out about that, conditioned on that result, his knowledge changes. And that's not unphysical. That's not a conflict with locality. That's just, well, then now we know what Bob's going to get from his experiment. We don't have to assume there's some kind of non-local force, right? So now, just a moment. So now Bell's point is, well, let's imagine that quantum states are not complete. Is there still a conflict with locality? And we're going to show the answer is yes.
Bob can do his measurement so soon after Alice, there's no way, like, he knew it was at space-time separation, so that he couldn't possibly receive the information from Alice. So how he therefore isn't updating on new information because he hasn't got any new information. How do you read the change of his state in that case? If you're on a Bayesian understanding.
Well, the point is that so an objective observer can predict the outcome of Bob's measurement.
From Bob's point of view, what's going on? Because he hasn't updated his
Yeah, no, for Bob doesn't know what's going on. Yes, I agree. But that's not relevant to the argument.
Has the state not changed for Bob? Surely you have to say it has, otherwise you're not going to get the right results.
I don't know what you're addressing. I mean, certainly if I have a ball and I have two boxes and I put the ball in one of the two boxes and Alice and Bob don't know which one it's in and they each get a box, okay, the fact that Alice opens her box and discovers whether or not the ball is in her box, and I promise you there's only one ball, there's nothing mysterious going on that we now, everybody except for Bob knows what's going to happen in his experiment, right? That's all I'm saying, is that there's nothing mysterious about that situation at all, right? So what we're going to look at here is something more subtle than that, okay? I don't know if that addressed your question. Did it, or I missed it? Okay, well.
But don't you get the right results because you don't know what the result of Alice's measurement will have been? I mean, so if you start in this entangled state and Alice measures hers, yeah, maybe it collapses Bob's.
Well, once Alice has done a measurement, you're certain what the outcome of Bob's measurement is going to be. And it's not clear to me what description, like how you encode that physically if there's nobody who knows the whole situation and therefore there's nobody actually updating their information.
So I mean, it's whose probability, right, is what you're asking?
Well, who's doing the updating?
Yeah. Well, Alice is updating her information. Just think of, okay, there's two scenarios. One is where we think of quantum states as physical and one where we don't. I don't know which scenario your question was, which framework was your question located in? The assumption that quantum states are physical or the assumption that quantum states are informational?
I'm questioning the story that you tell if you say quantum states are informational.
Oh, if they're informational. If they're informational, it's nothing different than the ball in the box. So whatever story you would tell for that is the story I would tell for
the information is, who does the information belong to, or what is the information about?
Well, I mean, it's each agent has some probability assignment about what will happen when Bob opens the box. But anyways, I think we haven't gotten to anything subtle yet. So let's just move on, and maybe you and I can untangle that question later. Okay, so all right, so this is, maybe people call this shocking, but so let's look at it more precisely. So here's our physical scenario. So we have a source. And that source is producing some output, which we believe corresponds to two particles. And then one particle goes into a box over here, and another particle goes into a box over here. So this box has a pointer on it, and we can choose setting A or A prime. And over here we have another setting, which is B and B prime. And then each of these, of course, has a readout. And our readout is going to be some needle, which points to 0 or 1. So we'll call this one Y. And this one, the readout is X. And it's also, sorry, it's not 0, 1. It's -1 or 1. This one is -1, +1. So this will be Bob's box. And this is Alice's box. And what we're interested in is we push the go button one time, and then Bob chooses some measurement, and Alice chooses a measurement, and then Bob gets ±1, and Alice gets ±1. And we're interested in how often these outcomes are correlated versus anti-correlated. I forgot my light. There's a light up here too. Okay, so we have, what are we interested in? We're interested in the probabilities. So we have we consider, we have the probability of some pair of outcomes, x and y, x comma y, conditioned on the detector settings, and conditioned on something called lambda. So here, lambda correspond to any physical properties that influence the outcome. So we typically think of lambda as being some hidden parameters associated with the source. Okay, so if we really had two back-to-back anti-correlated pairs of spins, then they would be, this would correspond to an angle specifying the direction of the spin. So we're going to assume that the detector settings A and B, we're just going to assume that they're either 0 or 1. And we have outcomes x and y in the interval -1 to +1. Now we can talk about there's a probability that we get outcome y conditioned on settings A, B, outcome x, and lambda. And there's a probability that we get outcome x conditioned on A, B, y, and lambda. So here we're allowing the probability of the outcome y at Bob's setup to depend on the choices of measurement by Alice and Bob, the outcome that Alice got, and the common cause physical parameters. So that's the most general thing we could have, the most general situation we can imagine. But we're going to make an assumption. We're going to assume we're going to assume locality, which is the following assumption, that the probability of x and y given a, b, and lambda is equal to the probability of x conditioned on a and lambda times the probability of y conditioned on b and lambda. Okay, so what's the justification for that? The justification for that is we say, well, look, we can imagine that these two are unconnected devices, and that we want to demand that we're in a situation where the outcome Bob gets depends on information from the source and depends on his detector setting, but it doesn't depend on Alice's choice of detector setting, and it doesn't depend on Alice's outcome. All right, so that seems like a plausible thing one can assume, and so this is motivated. This can be motivated from special relativity. If we imagine that, here's Alice, here's Bob. They both have a backwards light cone. Our source, this is our source. So our source is in the backwards light cone of Alice and Bob. It provides the physical state lambda, which lambda could include the quantum state, of course. And then Alice and Bob, then over here, Bob chooses, somewhere here, Bob chooses, say, B or B prime. And here, Alice chooses A or A prime. And then, of course, here, Bob gets outcome. Bob observes Y. And here, Alice observes X. So the idea is that Bob's outcome Y can only depend on things in its backward light cone. So we can break down the assumption of locality which goes by several names. It's also known as Bell locality, local causality, and or the assumption of local hidden variables. This last term is misleading because the variables lambda can correspond to the quantum state itself. So it's not clear. Calling them hidden is a little bit misleading. So these are various names for this. So it can be derived from two more primitive assumptions. From two elementary assumptions. So assumption A is that is called outcome independence. Which is that the probability of X given A, B, Y, lambda is equal to the probability of X given A, B, lambda. So we're saying that the probability of an outcome X does not depend on Y, and vice versa for Alice. Okay, so the term outcome independence is self-explanatory. And then the assumption B is called parameter independence. Which we can also think of as a context independence. And that's the assumption that the probability of X given AB lambda is equal to the probability of X just given A and lambda. And similarly, so here the idea is that the choice of measurement direction that Bob makes, whether Bob chooses B or B prime, can't influence the outcome X. So there's this, one way to think about it is free will. So we can think of this as a free will assumption. I mean, there are some issues here about thinking of it this way. Bear in mind that the idea is that in this picture that, you know, basically Alice is either choosing randomly between A and A prime, and Bob is choosing randomly between B and B prime. Now, if you take a criticism of that is, look, if I take a deterministic worldview, then really anything Alice chooses here or here, and Bob chooses here, ultimately traces back to a common cause at the Big Bang or something, right? So there's really no notion of free choice, of free will here that can be justified. So that argument is called the superdeterminism argument, which is that it's basically saying, it's like the superdeterminism loophole is saying that not only is it the case that Alice and Bob can't make random choices, or, I mean, typically what happens in experiments, you don't have some grad student named Alice picking a measurement direction. What you have is a random number generator or a pseudo-random number generator picking A or A prime. And so the superdeterminism argument is saying that, you know, things were contrived in just the right way at the Big Bang so that, you know, in 1970, when Alain Aspect did the first experiments, that the random numbers came out just right to seem to violate the Bell inequality or something like that. It's a very fantastic view of the universe we get if we want to not trust this assumption. But that's the parameter independence assumption. So I mean, the result is so startling that people really scrutinize both the theoretical assumptions that go into the derivation and the experimental validation of the quantum prediction are both subjected to, you know, greater scrutiny than any other quantum experiments. So I just want you to remark that there's a difference between if we just said the probability of xy given AB so in this type of setting, in general, if you have two outcomes, x and y, and two settings, A and B, the fact that the joint probability of x and y cannot be factored in this form is very commonplace, right? This is not surprising. This is just saying that there's some kind of correlations between x and y. There's lots of scenarios where we can imagine correlations between x and y, even classically with the ball in the box. I mean, if Alice finds the ball in her box, then Bob will definitely not find the ball in his box. That's a standard correlation. This is not surprising, but this assumption, this factorizability condition, is saying we're conditioning on all the possible physical influences that are relevant, are included in the probability. So that's why this is a more natural assumption to make under the space-like separation argument, because we assume that any possible influence is encoded as a condition on our outcome. But here we're not conditioning on all possible common causes. So it's not surprising that this inequality holds, because we can have, this is just typical correlations. X and Y are correlated. So just bear in mind there's a conceptual distinction between asking for factorization at this level versus asking for factorization once you say, I'm allowing lambda to be any possible cause that can affect the outcomes. There's a question in the back?
The argument about the universe being determined, what would make that affect quantum experiments, but not if we did this on a larger scale and tried to entangle things, tried to make the argument, oh, look, I can entangle two balls this big, and then if the universe is deterministic, couldn't you end up seeing effects that were mistaken for entanglement based on that? I don't know if I phrased that properly.
Yeah. Okay, I'm not sure if I understood the question.
The argument that because of the Big Bang, this determined all decisions of measurement choices.
Yeah, the superdeterminism. Yeah.
That argument, what I'm saying is, if that were the case, why would that only happen when we do these quantum experiments, but not if we did a similar thing, like taking, trying to have.
Oh, why? It wouldn't happen with classical objects. Yeah, well, I mean, you'd have to provide some. I mean, it's a conspiracy theory, the superdeterminism argument, right? It's saying, yeah, so it's saying this information was encoded just for, suppose over the course of human history we do 200 Bell inequality experiments with quantum entangled systems, then it's, those 200 experiments were pre-programmed at the Big Bang, but everything else we don't really care what was determined or not. It's a bizarre. It really, I mean, it defies the whole paradigm of scientific experimentation that, we can actually test different scenarios in a way that's independent. I mean, it just, so much goes out the window when you make that assumption. I mean, the point is you have to accept something strange because of Bell inequality violations. And it's a matter of taste which strange thing you're willing to accept. I mean, there's a number of assumptions that go into any no-go theorem, and so which assumption you're gonna blame? Oh, I blame assumption 3. I don't believe that's plausible. I mean, that's a matter of taste, right? And if an assumption has, if a theorem rests on 3 assumptions, at least one of those assumptions must be false. Which one we don't know. Sorry, was there another question? Well, I mean, the idea is that, I mean, we know about chaos and things like that, which is, the point is everything can be determined, but still be essentially random. Like a pseudo-random number generator is a deterministic device. But as far as practical tests go, it looks like the numbers are randomly distributed. So, for example, if you do some Monte Carlo experiment to probe some physics, and you get some result, and you say, I use this pseudo-random number generator, here's my result, I want to publish this in, Nature now. And your referee says, oh, I don't believe that this is correctly modeling physics because I'm assuming that at the Big Bang, your Monte Carlo generator was pre-programmed to exactly give this prediction, which is not actually random, but deviates from the true random prediction in a way that was predetermined at the Big Bang. I mean, you'd be like, what the heck? That's ridiculous, right? No, I'm just assuming I did a fair sampling of the random possibilities. If you're assuming that A and B really, the whole assumption is you really want the choices of A and A prime to be independent of the choices of B and B prime. Yeah, it doesn't have to be free will. It just has to be, you just need these things to be independent. You need the probability on any given run of getting A or A prime as the choice of measurement to be independent of the probability of B or B prime. And so you can have some crazy conspiracy that would lead to correlations between A and A prime, between A and B. But then, as pointed out in the back, well, why doesn't it happen when we do it with a ball in a box, right? Like in principle, if we have a ball in a box, or, well, that's not a good example. But maybe we can, yeah?
I was going to say that maybe it's just easier for those coincidences to happen on a quantum scale in the same way that quantum effects are more likely to happen. Like, it's just really unlikely for something this big to tunnel, and then the deterministic argument, maybe they would be like, for some reason, it's just also really unlikely for you to get lucky on the big scale, although I guess there's no real physical reason. I don't know, just like...
Yeah, no, I mean, I agree. I mean, there's some bizarre consequences, and it's not quite clear that. Now, mind you, the tension with special relativity is not an experimental tension, it's a conceptual tension. So special relativity tells us that signals cannot propagate faster than the speed of light. That's things that we can gain information from. And so the important point here is and we'll illustrate that point later, is that the kind of non-locality you need to reproduce the quantum predictions with like a hidden variable model are non-signaling. So Alice can't send information to Bob by choosing A or A prime. She won't affect Bob's ability to learn about her choice. So in other words, even in the quantum setting where there's some kind of correlation between X and Y that can't be explained classically, that correlation cannot be manipulated or controlled in order to transfer information from Alice to Bob. So, I mean, I think the most reasonable conclusion is that special relativity tells us about the propagation of information. And the non-locality implied by Bell's theorem is not about the propagation of information, but some other correlation of some sort. So the tension is only superficial between special relativity and Bell inequality violation. All right. Okay, so now so now we can define the probability of x, y given a, b as an integral over all possible values of lambda and then we can define the expectation of AB given lambda as a sum over all outcomes xy of the product xy times the probability of xy given AB lambda. So remember, x and y are outcomes, and so we either have +1 or -1 for each outcome, and so this product is either going to be +1 or -1. And then we're averaging we're averaging over possible outcomes. And that's the expectation given settings AB, conditioned on lambda. And then we can define essentially another expectation between A and B, where now we integrate over all choices of lambda. So this we're going to call just expectation of AB, like that. So now I want to make a claim. The claim is that if we consider this quantity S, which we call the expectation of AB plus the expectation of A with setting B changed to B prime, plus the expectation where A is A prime and we just have regular B, and then we subtract the case where A and B are both primed. We define that to be a quantity S, and then the claim is that S is bounded by 2 and minus 2. This is the CHSH inequality.
In one of the definitions, you have a probability distribution that weights the lambdas. Why don't you have that for the expectation value?
Oh, I forgot it is why. There. Yes? I'm sorry?
X and Y, are they discrete?
Yeah, so you can allow X and Y to vary between -1 and 1, but for simplicity, I'm just going to... The theorem works whether you would choose... Okay, so all results... Okay, so we can... We can assume without loss of generality that X and Y are in the interval -1, 1. Instead of X, Y having discrete outcomes -1 and +1. Okay? Yes? Oh, that is continuous. Yeah. Okay, good. What was the question then?
So when we're summing over X and Y, we're assuming that it's discrete.
Oh, I see. Right, right.
It doesn't affect the argument. It's a matter of notation.
Yeah, so that we could change that to an integral. Okay. was wondering if I should prove this. Yeah.
This quantity is, or are you considering that quantity? What importance is it?
With this particular sum?
Yeah.
Oh, well, the sum is derived. Okay, the importance is that here. Here's why it's important. So experimentally, we can define. Yeah, let's do that next. So experimentally, we can talk about the expectation of AB as the limit over some repetitions of the experiment. Each time we get a random outcome for x and y. And we take the average correlation, x in outcome n, conditioned on setting A, y in outcome n, conditioned on setting B. So this is now an experimental quantity we can measure. And then what we find, experimentally, we find that S can be greater than 2. Okay, and similarly, we can show that quantum mechanics predicts that S is equal to 2 times the square root of 2. So we make these innocuous assumptions about the fact that remote physical features that are outside of the light cone of Alice and Bob can't possibly affect the probability of their outcomes. We derive an inequality, CHSH inequality. And then we have that quantum mechanics predicts for an entangled singlet pairs, which I'll show you in a moment, predicts we should get 2 root 2 for this measurable quantity. And experimentally, it's been confirmed to be greater than 2 to within statistical precision many times. So let's look at the quantum prediction. The experiment matches the quantum prediction. So the quantum prediction.
One thing. So you're saying that this, I mean, you see why it is between -2 and 2 is whether both results are correlated or anti-correlated when I choose the same setting, or A and B, A and A prime and B and B prime.
Sorry, well, there's 4 scenarios, right?
Right. So where does the -2 and the 2 come from?
You want to see a derivation of that.
I mean, how do I prove that it's
So, okay, let me, all right. Okay, so let's look at a lemma. Let Q, Q prime, R, and R prime all belong to the interval -1, +1. Then S equals QR plus QR prime plus Q prime R minus Q prime R prime is in the interval -2 to +2. All right, so how do we see that? So S is linear. So here's the proof. S is linear in all 4 variables. So it must take on take on its maximum and minimum values. Where each Q, Q prime, R, and R prime take on extreme values. So this is right away, now we bias the discreteness condition is going to saturate the largest and smallest value we can achieve for S. Okay? And then, so this implies that S is an element of the set -4 all the way to +4. But we can rewrite S is equal to Q plus Q prime times R plus R prime minus 2 Q prime R prime. But here, Q plus Q prime can only be 0, -2, or +2. And similarly, R plus R prime can only be 0, -2, or +2. And the last term, -2 Q prime R prime, can only be -2 or +2. So S cannot equal ±3 or ±4. Hold on a second, please. Why is that true again? This isn't the way I normally do the proof, so this is, I'm not seeing why this follows right now.
If Q plus Q prime, and if the product is +4, then both Q prime and R prime have to be.
Oh, right, because this would be 6 or 2, and 6 is not allowed. Right, okay. Right, so this is either going to be 2, 6, or, oh, but this can be 2. All right, so this is going to be either 4 ± 2. Right, okay, I see it now. Does everyone see why that's the case? No? So the idea is that, look, this is going to contribute ± 2. We know that. So now, what are the possibilities for this product? Well, if this one is 2 and this one is 2, then we're going to have 4 or -4. If it's ± 2 or ± 2. But now we know that it can't exceed 4. So we're going to have something that's either ±4, ±2. But anything greater than 4 is impossible by linearity. Therefore, the only remaining possibility is 2. And similarly, if we have a 0, then this whole term will be 0, and this will be ±2. Is that? So it's a very simple, this is the way I normally prove this. The way I did it last year is a little bit different. But I was using a different notation, so it's probably better I don't try and reproduce that argument.
One thing, I don't know if what I'm going to say is true or not, but the CHS H inequality is for the correlation functions, right?
Yeah.
So here you're assuming that the average of A, B, A prime, B prime, all are 0. Because these are just a part of the correlation function, right?
No, AB, no, this is, each of these expectations AB is in the interval -1 + 1.
Yeah, but okay. I mean, actually, the quantity S isn't defined in terms of the correlation function.
It is. It's a linear combination of these correlations.
Yeah, but the correlation function isn't the average of AP minus the average of A times the average of B.
No, well, it's a linear combination of correlations. So, all right. So, yeah, okay, this is a lot to absorb, and there's a lot at stake, so I understand the concern. But we basically have a simple algebraic lemma which allows us to determine that S is bounded, the claim I wrote somewhere. Yeah, this claim here. Okay, so we can justify that algebraically under these assumptions that I wrote down, in particular parameter independence and outcome independence. Implies the factorizability condition. The factorizability condition guarantees that this sum of correlation functions. So here's the situation you imagine. We look at our paradigm. So we press the go button, Alice gets a result, Bob gets a result. All right, so think about the experimental setup. Alice gets a result, Bob gets a result when n equals 1. Then they do it again. And so each one is recording in their notebook each result they get. Then what we do is we take their notebooks later on, and we construct these correlation functions, AB, and then A prime, B prime is also equal to, we have a very large number of trials. We take the average product of X, A, N, Y, B prime, N. So we take their notebooks and we say, okay, now let's take all the random entries in the notebook where Alice chose A and Bob chose B. We calculate the correlation of their outcomes. We look at all of the rows in the notebooks where Alice chose A and Bob chose B prime. We calculate that correlation, and et cetera for the other two cases. And then we just take a linear combination of each of those correlation functions where we put a minus sign on the A prime, B prime one, because that gives an interesting result for no deeper reason than that. So that's what the experiment will be. So if you do this experiment with, back-to-back angular momenta that are anti-correlated, say, you'll find a result that's within 2 and minus 2. So everyone would expect this result between 2 and minus 2 for any physical situation. But now what I'm going to show you is that we prepare a quantum mechanical singlet and do measurements of spin at directions A and B prime, where A and B prime are chosen, A prime, B, and B prime are chosen carefully, then you can exceed this classical bound, this locality bound, which suggests that entangled quantum states have some kind of non-locality in them that allows a violation of one of these assumptions. Piers?
Can you extend this measure S to systems where you have, say, 3 settings you're measuring from? So say like A prime, A prime, and A double prime, B prime, B double prime?
So before I answer that question, why would you want to do that?
Well, because couldn't that correspond to, like, say, a tripartite system? Or...
It would not be a tripartite setup. It would just be a three setting setup. But why would you want to do that? Oh, because you were interested in connecting to tripartite entanglement. No, so there's a tripartite version of this called the GHZ inequality. So there is a tripartite version of this. Okay, so let's look at the quantum prediction. So we take our state to be the singlet state. So our Hilbert space is C2 cross C2. Our state is the singlet state. 0 and 1 are just labels. It could be plus a half and minus a half. It doesn't really matter. And we're going to construct the expectation AB as the expectation psi minus sigma dot A times sigma dot B okay, which is just the trace. So it should be clear that this sigma is a Pauli spin operator acting on system A. And this is a Pauli system operator acting on system 1 and system 2. So this is Alice's system and that's Bob's system. And I think I need some H bars and 2s in here. Let me just see where they go. Oh, right. So here sigma equals S divided by H bar and times 2. So we're just taking out, remember, well, let me write it the normal way. The spin operator S is equal to sigma H bar over 2. So we have, of course, sigma X is just the matrix 0, 1, 1, 0. Sigma Y is 0, I minus I 0. Is that right?
I think it's the other way around.
The minus is up here?
So, one thing before you proceed.
Yeah.
So you define this quantity as like this, right? In terms of variables that go between -1 and 1. So if I take the average of this inequality here, that has to be between -2 and 2, then it follows that S is bounded like this, right? But how can this differ in the case where I take the average with probability distribution associated to a quantum state? Right? In this case, this is what you're going to do, right? Calculate this correlation function, like bracketing with psi minus, right? So this is just, I mean,
It doesn't matter. Here, the point is this. Quantum mechanically, how do you measure this? So quantum mechanically, in QM, we measure this in the same way as classically. We measure the quantum expectation AB is equal to the limit as n goes to infinity of 1 over n, sum over n, x, a, n, y, b, n. I mean, this is experimentally what we do to measure this quantity. So the point is quantum mechanics makes a prediction, which we measure in this way, this is the standard way to measure a quantum expectation value. Of course, you can never take the limit n goes to infinity, so the right-hand side is always an estimator of the true mean correlation. But we can make that estimator as precise as we want by just repeating many times. And then the question is, so quantum mechanics makes this prediction, which we measure in this way. Can we understand this expectation as a consequence of averaging over some unspecified degrees of freedom? So yes, we can. But now if we assume those unspecified degrees of freedom lambda so we assume that, then we assume moreover that the probabilities depend only on lambda and the local settings. Then we get this bound, wherever it's written, the CHS inequality. CHSH, so it's Clausi, Horn, Shimoni, and Holt inequality. And now what we're going to show is that the quantum prediction and experimental evidence violates that inequality. So one of our assumptions is wrong. So let me give you the specific setup. So B, A, B prime, A prime. Okay, so for maximal violation, that's S equals 2 root 2. So this is 45 degrees. And this is also 45 degrees. It's A, B, A prime. Let me just make sure I got the labels right. B, A, B prime, A prime. Sorry. Yeah, that's fine. So if you choose these directions, these vectors, all coplanar. So we have 4 coplanar vectors for our direction of measurement. So what this means is I do a poly measurement at on Alice's system at this angle or at this angle, and Bob does his measurements. I mean, they have a shared reference frame. Bob does his measurements along B or B prime. So they're both 90 degrees apart, but they're offset by 45 degrees relative to each other. And then this is a straightforward calculation. So I'll leave it as an exercise. You can calculate this. Do this quantum calculation. So this is what all the fuss is about. Oh, I should also mention in this setting you get AB is equal to 1 over square root of 2, which is also AB prime, A prime B. And for A prime, B prime, you get minus 1 over square root of 2. By calculating, evaluating this expression. So let me tell you a little bit about experimental confirmation of this. Yeah. Go ahead.
So I see where we use the assumption of locality, obviously, where do we use the assumption that it's incomplete? Is that in introducing lambda parameters?
Yeah, we're introducing an additional specification. So lambda could just be the quantum state, in which case the result works. But we could assume that in addition to the quantum state vector, there's also some other degrees of freedom that we don't know about. You know, the project of physics is unfinished.
So if you hadn't included lambda, you already put it in.
If I had not included,
If you had not included the lambda parameter, where
well, I mean, you could just set lambda equal to some fixed value and make the probability density a delta function on that fixed value.
for that reason, it's not very well
Which is,
the quantum physics.
oh, so I mean, okay, I think that, look, you can drop that assumption and you still can get a contradiction. But the point is, we don't need this complicated scenario to demonstrate a conflict when we drop assumption 2, because we already have that from EPR's argument. If we just assume locality in the quantum mechanics is correct and the quantum states are complete, we already have a contradiction from EPR. Not just complete, but they're complete and physical somehow. They correspond to some physical property of the world. That physical property changes non-locally just from the state update rule. And so it's kind of what Bell said. Well, even if we drop that assumption that they're complete, then we still have a conflict. Yes?
On that note, is it sort of like if we had some entangled or some state in the product Hilbert space, and therefore it's a linear combination of these separable states, lambda tells you which separable state you were in. Like it's sort of lambda means, oh, when we're in, like it's correlated, but we know which. We don't have to worry about different possible separable states where we know which one it is. So like that, or is that too?
Can lambda be parsed as that?
Yeah, that's what I'm asking.
Yeah. I don't know. That's curious because they're. I mean. No, I mean, I don't know. I don't know how to make that fit. I'd have to think about it. Okay, you know what? Okay, so look, it's been experimentally confirmed lots of times. You guys can read about it. The first really decisive experimental test was done by Alain Aspect in the early 1970s, and it's been repeated many times. People are now pushing the boundary of trying to close various loopholes. So, I mean, physicists have a lot of trouble with this result. They kind of want to not believe it, so they put forward kind of, conspiracy theory arguments against the experiments that they're not. I mean, it's kind of strange because the experiments are just telling us that quantum mechanics is right. So if you're like denying the experiments based on loopholes, then you're kind of saying, well, it's because quantum mechanics is also wrong and doesn't predict what the experiments are confirming. But the kinds of the kinds of models people have concocted to deny the experiments are things like the fair sampling loophole, which says that your detectors don't always function perfectly, right? So if I receive a photon, typically these experiments are done with photons, correlated light pairs, entangled states of light, right? So yeah, so the point is, every time you receive a photon, you don't detect it. Lots of photons go undetected because detectors don't have high efficiency. Like maybe a typical figure would be 80% efficiency of a photodetector. I mean, there's a wide range depending on the type of technology you use. And there's typically a trade-off between what are called dark counts and detector inefficiency. So dark count is the detector clicks when no photon went in due to thermal activation of the mechanism. So it actually says I saw a photon when it doesn't, and that's a dark count. And then detection inefficiency is that a photon arrives at the detector, but there's no click. The detector says it didn't see anything. So that's a detector inefficiency. So people argue that if the detectors specifically didn't click for a special subset of the experiments, then you can, if you have a conspiracy and they know in advance not to click for certain settings, or it's some crazy scheme like that, then you can show that the experiments don't actually violate the Bell inequality, the CHSH inequality. So, I mean, I don't see much value in worrying about that, but if you're interested, there's a whole like sub community that worries about this, and then people go and do the experiments with higher and higher efficiency detectors to close the fair sampling loophole. I think it's actually been closed just within the past few years. They use detectors with high enough efficiency that they said, look, it doesn't matter. There's no conspiracy that can overcome this. And then the other loophole is the communication loophole, which is, you have some source which produces pairs of photons, and the photons leave the source, and then you actually have some electronics where you're pseudo-randomly generating the choice of measurement. And what they try and do is make that so fast. The problem is that the actual choice is made not really outside of the light cone of Alice and Bob's detectors. So what they do is they buy very expensive electronics so that they can make the random choice of A or A prime in such a way that it's outside of the light cone of Bob's measurement decision and vice versa. So that's the communication loophole. And so I think that's been closed as well. But I think that there's been no decisive experiment which has simultaneously closed all loopholes. So there's still hope for the deniers. Yeah?
I'm still missing to understand something. So if I don't refer to this assumption of locality or anything, I can also prove, the proof of the CHSH inequality is independent of that assumption, right? Of locality.
No, it depends on it, critically.
Oh, it does.
You have to have the factorization.
Why?
Factorization is essentially
The point
I mean, if I take this function as to be a function of q prime r prime, right? And I prove that it's bounded by -2 or 2.
Hey, where did that come in?
Here
Hold
in
on.
your lemma, right? Now you have that function, right? Now, what is the step to say that?
Yeah, that's a good
where does
question.
the locality assumption enters into play to show that in fact that?
Oh, yeah, it's a good question. I don't remember now.
Because what I'm saying here is just you're using just a rule of probability
Because you calculate the
where you're
correlation.
not, I mean, you're not
If you actually
assuming,
want to calculate the correlation, you
correlation
should be able to
fractions
factorize
by
the
using
probability.
factorization.
what?
Well, that step isn't explicit anyways. Let me just
I
check.
can take this S that is bounded by minus 2 and 2, take the average of this, right? And if it's bounded minus 2 and 2, the average is a linear function. So I hope that the average of each of these terms in that S function there is bounded by minus 2 and 2.
The correlation function will
Right.
have a different value if you don't assume factorization because you can get the additional correlation.
No, I'm just taking QQ prime R and R prime to be random variables between minus 1 and 1. I construct this function that is called S. It's bounded between minus 2 and 2. I take the average of this function. It should be bounded in between minus 2 and 2. The average is a linear function, so I get the CHSH inequality without making any assumption of locality
I'm
whatsoever.
not sure that it would be a linear function if the correlation is correct.
The correlation is just an average, right? Of this QR R and QS prime, whatever. Right?
And the idea is that you can get additional correlations that don't, so they don't split up in the right way in order to make those functions independent.
Right, you need Q and Q prime to be independent. Right, so let me just add that here we take, here Q is defined to be a sum over x times the probability of x given a comma lambda. And so Q prime is defined in terms of A prime. Change of notation. Oh yeah, R is equal to sum over Y.
I think you may also need to integrate out the lambda.
Defining my correlation like that.
Yeah, I need to integrate out the lambda as well.
That correlation function is independent of my lambda, right? On my hidden variable, whatever it is.
No.
Yeah. It's just a product rule. I mean, it's the marginal property.
But the point is that you're not allowed to use the product rule because you can't allow them to factorize unless they are.
The product rule is independent whether my variables are independent or not, right? Where I have rho of lambda, the probability of x, y given a b lambda is the same as the probability of x, y and lambda given a b. If
I think
sum
you
of
still
all
have
that
to
over lambda, I
integrate
get a marginal probability.
over lambda after multiplying together, multiplying everything together.
Oh, you have to multiply first and then integrate? Is that the?
Yeah.
So this is Q of, that's what they do. No, that's what, yeah, that's what they do here. So let's follow that. Right, then we integrate later. So it's true for each element of the set. It's going to be true for the average. Yeah, I assume this comes in via the linearity in the four variables because they're independent variables. And so that's what buys us this bound here. So how can you deduce, and this here we use the factorizability condition.
You do it in terms of expectation values, and you say that expectation value of QR is equal to expectation value of Q product expectation value R, which is not the case if the Q and R are correlated. So you can't make that separation if they're correlated. Because you don't just want S, you want the expectation value of S over many experiments. And so you can only split them up into independent variables as the expectation values if they're independent.
Okay, you know what we'll do? We'll return to this at the beginning of next class. I have a different way of normally proving it, and I was using this proof, which I'm not as familiar with.
So, I mean, the lemma.
So,
I mean, if I jump from the lemma to the claim, then I mean the inequality is somehow. No.
Because it's the expectation value of S over many experiments. And so you split it up into a sum of expectation values, and then you need to split it up into each sum needs to be a product of two expectation values in order for this to hold.
that it's not good. That's not. If you can't split.
Why do I have to?
You can't split it
Why,
into a
why
product.
do I have to put it in terms of the product?
The expectation value of Q times R is not the same as the expectation value of Q times the expectation
Right, I
value
know,
of R
but
unless
you don't
they're
need that.
independent.
You don't need that if you're defining.
Yes, you do, because then it's
The
going
limit
to
of
be
one.
each won't be linear in all 4 variables if they're not independent.
Yeah, I mean, I think the factorization buys you this very first step. And then the rest just follows from algebra. But I mean, this is subtle, so let's revisit this at the beginning of next class. And it gives you some time to think about it. And we'll make it more explicit.
So, okay, another question.
All right, one last question.
Let us assume I understand. Now I have this inequality for this case, right? And now in quantum mechanics, I have a maximal violation when I choose my setting in this way, right? What's the importance of it? What is the importance of it? I have a result in quantum mechanics. I have a result in classical mechanics. Where is the contradiction of being quantum states being real or not real? Or
The importance is the locality assumption. That people don't like the idea that quantum mechanics has to be fundamentally non-local. They're hoping that they'll be able to build in some variables or something that can make it local.
so, but then how does having this result implies that
This result
I have
implies
something
that
wrong with locality?
because factorizability doesn't hold unless you've got locality. And so if you have locality, you expect factorizability, and therefore you expect this inequality to hold.
Right.
So if the inequality doesn't hold, you have to assume, if everything else follows, if all the other assumptions are correct, you have to assume that locality fails, which people don't like.
I mean, loosely speaking, the probability, I mean, here's the point, is that the upshot of this is the following, is that the probability of Bob's outcome, given his choice of measurement, depends on which measurement Alice chose to, which measurement direction Alice, no matter if they're space-like separated or any other conditions. So there's another thing I wanted to do, which is this CHSH game. So I can show you how to turn this into like a game, which you can win only if you have access to quantum particles. We'll talk about that as well next class. All right, good. Thanks for your attention, and see you tomorrow.